So we're going to talk about heat transfer from extended surfaces. We are going to actually go more into like applications of heat transfer, and I'm pretty sure that you're familiar with the computer chips, at least. I mean, you know that they actually heat up, and there are elements that actually cools down these chips. There are actually fans installed inside the computers, which actually make those chips cooler so that they can work at a suitable temperature. And and most of the time, almost always, I guess, the computer chips are equipped with extended surfaces, what we call as fins. Example system. Fins to improve cooling on computer chips, right? So imagine you have a chip like this, and you just want to increase the heat transfer to, I'm sorry, to make it colder, so that you actually attach some extensions, which are called as fins, right? Okay, one can draw it in a much nicer way, but these are what we call as fins. Okay, so that the structure has a larger surface area, so that the cooling can be made faster. Made faster by increasing the surface area. Okay, so that's the trick. Yeah, you can do that, but why are we gonna model it? I mean, just put some extended surfaces and just see whether it's gonna do the job, because we want to actually design systems. If you want to design systems, you need to understand the mathematics behind it. You need to come up with equations that tells you how large should a fin be to provide, like, to keep the temperature at, for example, at a T set, right? And you need to also model how fast the heat transfer is, and how much heat is being actually lost, because you might actually need it depending on your problem. Okay, let's study heat conduction in a cooling fin. And in order to make the problem simpler, of course, we are not going to put a bunch of fins there. We're just going to focus on one particular fin so that we understand it much better. Then you can actually scale it up with like so many fins. So I'm going to have a schematic for one fin. This is the body, which you could call as the wall. Okay. And this is your extension. This is the extension of the structure. Okay. And let's talk a little bit about dimensions. So this fin has a length of L. It has a thickness of 2b. Well, actually, we're not going to lose anything if we call it b. Let's call it b. Okay. And we have a width of w. Okay. And one thing I actually would like to ask at this point is, do you know why we are actually working with like symbols instead of numbers? Like, why am I not like coming up with an example saying that like 20 meters instead of L, or maybe 10 centimeters instead of L, and 1 millimeter for B? Any idea why am I actually starting with awkward symbols and variables instead of numbers?
Is it because if you can apply it to any other situation? So like if the number changes, the L's still there, so it's just plug and play?
Exactly. You can. One reason is you can actually apply it for general cases, for any case when L changes. Another reason is basically if you plug in numbers, if you start with the numbers from the scratch, from the beginning, then you're not going to be able to do dimensional analysis at the end. And so, for example, if you find that the heat transfer rate is 20 like watts, right? There's no way you can do like you found 20, and there's no way you can do the dimensional analysis with that. And because you don't have a formula, or you cannot do like limiting case analysis, you have no idea about how the formula looks and whether it's consistent with expectations, right? Okay, good. Yeah, so we want to solve it for the general case, and we want to understand the system instead of like a particular problem solved for a particular chip or whatever. Okay. So okay, so I want to find out the temperature profile, heat transfer rate, like how fast it cools out, and so on and so forth. Now, let me give you the coordinates. We're going to work in one dimension. So this is your x, dimension x. This is where x is equal to 0. Okay. This point is where x is equal to L. Okay. And I need to do it before everything else. Actually, let me list a couple of things here. I'm going to assume that it's going to be steady state heat transfer. I need to simplify my problem, and the first thing I declare is that this is a steady state heat transfer. This is a plausible assumption because most of the cases you have like your equipment running for a long time, so that it actually comes to the steady state, and generally you're not actually interested in the startup conditions. Sometimes you are, but let's solve for the steady state, much simpler problem before you even try to solve for a transient problem. Another assumption is T varies only along X. Okay, meaning that the temperature here is the same as the temperature here, but the temperature here is not the same as the temperature here. So there are variations in this direction, but there are not any variations in this direction. Okay. Later we are going to see that this corresponds to a dimensionless number being much smaller than 1, which is called Biot number. Later can be justified right using Biot number. We're going to talk about it later. not now. Okay. And the task is, let's derive the temperature profile for the case where W and L are much larger than B. Okay. What does it mean? It means if there's any heat loss along this direction, it's much more significant than any heat transfer along these directions. Okay, so you can actually assume that most of the heat transfer is through the top and bottom surface of this thing. Okay. Okay, good. And one more thing. So this is gonna be cooled by the air, right? Either by stagnant air, or you're actually running a fan. It's forced convection, or yeah, it's either forced convection or it's natural convection. But you have some sort of associated H, right? H is the heat transfer coefficient, and TA, or let's call it TF. You can call it TF, T fluid temperature, or you can call it TA, air temperature. Okay, so I have the fluid temperature TF, and the fluid has heat transfer coefficient H. Now let's go ahead and model it, and then once I derive the temperature profile, I'm gonna just look for the heat transfer rates and so on. Okay. So let's write it. Yeah, find heat transfer rate from the entire fin, or in other words, total, maybe heat loss rate, rate of total heat loss, right? Okay, so we set the stage. Now we can start. We're gonna take it a shell, right? And is there any suggestion on how to take the shell? Should I take a shell something like this? What do you think? Now, one thing very important when you take the shell is the shell, within the shell, the temperature should not vary. So if you take a shell something like this, the temperature here is going to be different than the temperature here. So that's not a legitimate shell to take. So you need to take it like this, because the heat transfer is mostly, the temperature is varying mostly along the x direction. So if you take a slice like this, you can assume that the temperature here is the same as the temperature here, and that's the same as the temperature here, and so on. So you can actually assume uniform temperature along your slice. That's my primary concern here. Okay. Any questions so far? I didn't give you the the thermal conductivity. Thermal conductivity of the fin. It's K. Okay. So let's call it K. Okay, good. Now we took the shell. Now we're going to talk about how much heat is being inputted. So this is going to be the heat input. heat entering the fin, entering your shell, right? Let's call it Q at X, Qx at X. And then the flux getting out, let's call it Qx at X plus delta X, right? And if you do the shell balance gives in minus out plus generation is equal to accumulation, right? And the accumulation is 0. Why? Because I assumed steady state here. And there's no generation because we want to cool down the system. We don't want any like extra heating elements there. So on the fin, there is no heat generation. There might be heat generation on the wall just because like this chip is like running on electricity and it might actually heat up due to generation. But since my shell is not here, but here, the generation within my shell is 0. Okay. And in minus out, this is like rate of in. This is rate of out. You can also think about like total in and total out. That would be a different shell balance. But let's, for the time being, let's talk about per time input and per time output and per time generation, per time accumulation. Okay. So you can call it like rate of in, rate of out. Okay. And the rate of in is basically Qx times the area. The area of this shell is basically the cross-sectional area of this shell is the area of that rectangle, right? This area is nothing but B times W, correct? So you have BW estimated at, at X minus out is Qx BW estimated at X plus delta X. And the reason why actually I'm having this X plus delta X outside of the parentheses instead of just next to Qx is because my B and W generally might change with the X. But for this problem, it's not changing. That's okay. But we should not take it as granted in the beginning. Maybe you can do this assumption later. But it's always a good idea to keep like everything, the flux times area within the parentheses, because sometimes these terms might actually depend on X. So you would get a different BW for X plus delta X. For example, if you had a fin like this, right? Your shell actually would shrink, and B and W would be a function of X. You would call it BX and WX, and you should definitely have this X plus delta X there. Okay, so that's the reason why actually I am accustomed to keeping everything within parentheses and writing X plus delta X outside. Okay, good. That's equal to 0. And I'm going to divide by delta X and take the limit delta X goes to 0. Okay. So this is still 0. And this thing is the minus derivative of whatever you have inside the parentheses. It's Qx B. Oh, I forgot something. I'm sorry. Let's go back. Let's go back. Let's see. It's a big. Yeah, that's a big. I forgot something. I'm sorry. Here. This is not the only heat output. So you have one input here, but you have 2 outputs. Let me write down specifically. Another output is basically, this one. This is also Q out. And it's basically the convective heat loss minus how much of heat is being lost there. It's the heat transfer coefficient H times the temperature difference T at X, right, minus T of the fluid times the area, the area which is exposed to the air. Well, it's basically the perimeter times the thickness, P times delta X, and P is the perimeter of the shell, and it's basically 2B plus 2W, right? 2 times B plus W. Yep, there you go. And that's equal to 0. Now I have everything there. I have the conductive heat input, conductive heat output, and convective heat loss. And the reason why I have this minus here, it's being lost. And the reason why I have Tx minus Tf, because I want to make this positive. And for this problem, I'm assuming that my fin is hotter than the fluid. Okay. If your fin were colder than the fluid, you would get the same expression, but it would be like plus H Tf minus Tx. But then you can actually play with the position of this 2 and make this minus. You would get exactly the same thing in that case too. So it doesn't matter which way you think, whether the fluid is hotter or the wall is hotter, you get the same equation. It doesn't matter. So we are not actually making any assumption here about which one is hotter, which one is colder. Okay. Now we can divide by delta X and take limit as delta X goes to 0. You would get minus d over dx qx bw minus h tx minus tf times perimeter, which is basically 2 times w plus b. That's equal to 0. Okay, we're almost done. We're going to plug in Fourier's law.
Are you missing a delta X?
No, I divided everything by delta X.
Oh yeah, okay, thank you.
So this also actually canceled. So I got rid of this. Okay. And the delta X, when you divide this one, you just have it in the denominator. Here it's the derivative, right? Okay. Let's plug in the Fourier's law. It gives you Qx is equal to minus conductivity of the fin times dt over dx, right? And let's plug in this here. You get the following: plus k, and considering, let's say, and considering b and w constant, k times bw d square t over, I'm sorry, d square t over dx square minus h tx minus tf 2 times w plus b is equal to 0. By the way, this is also tx. Okay, t is a function of x. So if you actually solve for d squared t x over dx squared. You collect everything else on the right hand side. You would get 2hw plus b divided by kbw times tx minus tf. Okay. So that's the governing equation. Seems complicated. Let's simplify it a little bit. To replace the like big, let's say the chunk of constant terms. Replace the chunk of constant terms by a single constant number. Okay. 2 by non-dimensionalizing the equation. Okay, so we're going to do two things. First, let us call lambda square as this 2h w plus b over k e w. So we did nothing but actually called this thing lambda square. Okay. And the reason why I used lambda squared instead of lambda is basically I don't want to forget about the fact that that constant is a positive number. Okay, that's very important to keep in mind, that this is positive. Okay, so if I call it lambda, maybe there's just I will forget about the fact that it's negative, positive. The reason why this is important is because we're going to solve a differential equation, and it matters whether the constants are positive or negative. You can get two extremely different answers for a differential, for two differential equations. One has positive, the other has negative coefficient. So let's call this as lambda square, and then let's also non-dimensionalize. So let's first do this step. D squared t x divided by dx squared is equal to lambda square tx minus tf. Looks much simpler. But this is a formula which relates like temperatures, positions, and so on. They have units like Kelvin, meters, and so on. But I want to make everything unitless. So let's define dimensionless quantities for temperature, let's call it theta, the dimensionless temperature, and let's we'll actually write it in terms of T, TF. Oh no, not TF. Yeah, maybe TF. So when you dimensionalize, you ask the following question: what are the characteristic temperatures that I have in my hand? You see the TF will be given to you, and the wall temperature TW will be given to you, right? Okay, let's call that the TW is given. Okay, so I'm going to actually generate this theta using T, the temperature at any point, and reduce the dimension using the TF and TW. Okay, so I'm going to construct something here. So watch for that. I can basically do like ratios of the temperature to make it dimensionless. For example, I can say T divided by T wall. You can say that this is dimensionless. But basically here you're not making use of the TF. Maybe TF is also an important temperature or important characteristic for this problem. So what you should do is basically you should include the TF in your calculation too. So another actually possible way to make a dimensionless quantity is to do T minus TF divided by T wall minus TF. Okay, and the reason why I'm actually subtracting this TF is basically, look, I have something like this here already. So I can actually make it pretty easily look like the one appearing in the equation already, right? So let's call this theta T minus TF divided by TW minus TF. This is both dimensionless and also making use of all characteristic temperatures of the problem. In other words, TF and TW. As I said, you could have done like T minus TW divided by TF minus TW, but I don't have the T minus TW in my governing equation, so it might be really difficult. I might get a more complicated equation, so that might be much better. So let's non-dimensionalize the position. Instead of x, let's use psi, this fancy Greek symbol, is equal to x divided by L, because the only characteristic position that matters in this problem is L. That's why I actually divide the x by L. Okay. Because the heat transfer is majorly happening along the x direction. More correctly, the temperature is varying along the x direction only. So since my temperature is a function of x, and I want my theta to be a function of psi, then I just want to rescale it using the L instead of the B's and W's. Okay. So let's actually convert this to d squared theta over d psi squared. Okay, so you're going to convert it to that form. And in order to do that, I'm going to start from d squared theta over d psi squared, and let's see how many d squared t over dx squared is that, or like what is the conversion factor between the two, right? This is basically nothing but the second derivative, or one derivative followed by another derivative applied to theta. Now I'm going to plug in these expressions, theta here and the psi here, and also here, and I get d over d x over L, d over d x over L. In parentheses, the theta is T minus TF divided by TW minus TF, right? And from here, after I make these 1 over L's upside down, that's going to be L squared over T wall minus TF. That's constant. I can take it out of the derivative, but the derivative of t minus tf is the derivative of t only because you're just subtracting a constant. So this is nothing but d squared t over dx squared. Okay. So I wrote this in terms of this. So you can solve for d squared over dx squared instead. Thus, d squared t over dx squared is equal, can be replaced by tw minus tf divided by L squared d squared theta over d psi squared. Okay. Now you can replace this thing over here. But what about this one? You should also replace t minus tf2 and t minus tf is nothing but, from here, theta times tw minus tf, right? And you can actually plug this in here. Then you would get the following. tw minus tf divided by L squared d squared theta over d psi squared is equal to lambda squared tw minus tf times theta. And now the equation simplifies because I have this t wall minus tf here, t wall minus tf here. Then my equation becomes d squared theta over d psi squared is equal to lambda squared L squared theta. Perfect. I have some, what's that? I have some positive number here. Okay, good. So this is my governing equation. Governing dimensionless differential equation. Okay. So, well, basically, this is dimensionless. This entire thing. This is dimensionless. This is dimensionless. This is dimensionless. But I know that the L has the dimensions of meters, so the lambda must have the dimensions of 1 over meters. So they cancel and they give you a dimensionless number there. But that's not a problem. You can just assume it as something like a constant. Now, from analytical, I guess, analytical methods, probably you know how to solve this equation when this when the second derivative of a function is equal to itself times some positive number. You can write it in terms of like exponential functions, right? You can write theta is equal to, theta can be a combination of exponential lambda, sorry, not lambda square, lambda L psi plus some constant C2 exponential minus lambda L psi, right? Or any combination of exponential plus and exponential minus, you can write it in terms of sine hyperbolic and cosine hyperbolic. And instead you can say it can be C1 sine hyperbolic lambda L psi plus C2 cosine hyperbolic minus lambda L psi, but not necessarily the C1 and C2 are the same C1 and C2. So let me call the previous ones as C1 prime, C2 prime, but you can actually come up with C1 and C2 in terms of C1 prime and C2 prime if you know these numbers. because you know that the sine hyperbolic and cosine hyperbolic are already like linear combinations of exponential plus and exponential minus. Just a reminder. Sine hyperbolic x is equal to e to x minus e to minus x divided by 2. And cosine hyperbolic any function is equal to e to x plus e to minus x over 2. The reason why they call them sine hyperbolic, cosine hyperbolic, they actually don't have anything to do with sine and cosine. Well, actually, they have it very indirectly, but they resemble the properties of sine hyperbolic and cosine hyperbolic resemble the properties of sine and cosine. When you take the derivative of sine hyperbolic, you get the cosine hyperbolic, and derivative of cosine hyperbolic is the sine hyperbolic. And the sine hyperbolic 0 is 0, while cosine hyperbolic 0 is 1. So they actually look similar, although they are completely different functions with different natures. Okay, so this is our dimensionless temperature profile. Dimensionless T profile. But something is missing here. C1 and C2 must be determined from boundary conditions. Okay, so we're going to do that after we give a break. Okay, so after break, let us complete finding T profile. Okay, and then estimating the heat loss rate. Okay.